Hello, this is Jack Jackson. In this video, we're going to be talking about surface area of a surface of revolution. So earlier in our videos and our notes, we examined revolving an area in the XY plane, a region that had some area, and then we revolved that around a vertical or horizontal line to produce a solid of revolution. We found the volume of such a solid using the washer and cylindrical shell methods. So what if instead of a 2D region with some area, we revolve a curve in the XY plane about a vertical or horizontal line? This will produce a surface in 3D, and naturally we would like to be able to compute the surface area of this surface of revolution. So let's start by thinking about what would happen if we just revolve a line segment about a line not containing the line segment. What shape would result? So let's start by having the axis of rotation go through the endpoint of the line segment. And so I'm going to use this activity here that you can see a link to here, which looks like this. So I'm actually going to go to that activity. Here it is. So here I'm going to take 2x from 0 to 4, and the line is going to be the x-axis. And this slider here will show you over here on the left what happens when you start rotating that around. And of course, what do we end up with? Well, we end up with a cone. All right? Finite cone. Okay? So, we want to figure out what the surface area is of that cone. Okay? All right, so I'm going to look at this activity here to look at the surface area of a cone. I have that pulled up as well. So here it is. So here's a cone right here, and we're going to see what happens if we were to slice this thing open. So they're taking the idea that this has a flat top to it. We're not going to find the orange area, but only the blue area, the lateral surface area. So we're going to cut this down this place here and then wrap it out. So first of all, we're going to peel off the top. They're going to slice down the side of the cone and unwrap it. And look what happens when you unwrap it. You get a circular sector. In this, we can change the radius. Notice as you change the radius, you're not changing the lengths here, which is the slant height, but we are changing the how big this is. So this, how big this curve is right here is, remember it was originally wrapped around that circle. So it is the same length, this arc length of this arc of the circle is the same as the circumference of that little circle. Now there's two different radiuses going here. The radius of the circle here is what we're going to call R, and the radius of this circle we're going to call L, which is the slant height here. And notice that we have a Pythagorean relationship between the height of the cone, H, and R and L. Here we can kind of change the height, which changes the slant height. Okay, so let's go back to our notes now. Okay, so now we want to find the area of this blue region. Well, so again, this side is L. So the central angle, let's call this theta right here. So we have the area of this is proportional to that angle. In other words, that area is to the full area of a blue circle if we would finish it all out. Well, that blue is pi times the radius squared. Well, the radius here is L. So pi L squared is the radius of a full circle, and we have a fraction of that. So A is to that as theta is to the full angle going all the way around, which is 2 pi. So solving for A here, we multiply by pi L squared on both sides. The pi's cancel, so we get 1/2 theta times L squared. All right, now let's think about relationship here. The arc length of this circle here is just theta times its radius. So theta times L is going to be the arc length here. We measure in radians. That's basically how radian measurements work. Okay, so that gives us a relationship there. So if we substitute that in, theta times one of these L's is S, and then we still got the other L in the 1/2. So the area is 1/2 SL. So it's 1/2 the slant height here times that arc length. Okay. So R is the radius of the orange circle, then S is 2 pi times R. So this arc length here is 2 pi times is the circumference of this circle, which is 2 pi R. So I can substitute that in. So 2 pi R goes in place of S. The half and the 2 cancel, so you get pi RL is the area of the blue area, and that's what they've got here. They're saying that the surface area is pi RL plus that area of the base, which is pi R squared. Okay, but we're only interested in the blue part, so it's pi RL. Okay, now what is R? Well, going back up here, R is going to be the radius of this outer edge of this circle that makes this outer edge. Well, that's the distance from this point to the axis, which in our case is well, it's 8 at the moment. Okay, and so I guess we should say in the following example, we take a thing here. One is not the length L. So L is going to be the length of the original segment, and well, in the following or the previous example, L is going to be the length of the original segment. R is the radius at the end of the farthest end. So looking at this picture, L is, well, whatever that is. It'd be that we could figure it out by the Pythagorean theorem, I guess. This is 4 square plus 8 square, and add them up as square root of that. That would be that length. And then the radius would be from this point up to here would just be 8. Okay, now, so we can look at that. Okay, so let's see, where are we? We're down here. Now let's change it a little bit. We'll change the function to the square root of x, and let's make it where the line doesn't touch the endpoint. So generalize this just a little bit. Okay, so now we're going to go to just say square root of x, and we're going to go, let's see, let's just add one, let's say, scoot it up a little bit. And now what do we get when we get a shape? We get a shape that looks like this, and you can see it rotating around. So it's part of a cone, right? It's a cone. It's like a cone that we had before, but then we've cut off the bottom part, which we've cut off a cone. So it's a cone minus a cone. Okay. So let's look back at that and see what we can do with that a little bit. Okay. So basically you've got this picture here. Now this is these are, I didn't take time to make these two in scale with each other. Okay. But let's look here. Here is the cross section of the cone. So we put the cone at the top here. This is our original distance S. So now we're going to call the length of that curve S. So in our picture, that was the length of the line segment. This is the x-axis right here. And then we're going to rotate it around. So I've kind of flipped it around and flipped it over. And this rotates around here. So the part we're going to get is rotating this red piece. But if we were continue it all the way back to the x-axis here, we'd be rotating this blue piece, which I'm going to call L1, for a slant height of a full cone. And so we would get a full cone here to here, or finite cone anyway. All right, and then we would cut off the little piece by rotating this piece out to here, which is from here to here. All right, so that would be L2. So it's the cone we get from rotating the L1 minus the cone that we get from rotating L2, minus those surface areas, right? Okay, and that's going to give us the surface area that's left by rotating this red one. Okay, so if we kind of fold this out, this is what we see. So the full area by rotating this line segment all the way from here to here, or from N to P, or from N to O, that's going to give us this full shaded region, including the darker and the lighter shaded. Okay, now what I want to do is just rotate the smaller piece, the black piece here, and that gives us this one here. And notice if I subtract that from the other, I get what I get by rotating the red piece. So we're looking for this kind of lighter shaded area here. So we're going to do it by a bigger area minus the little dark area here. Okay, so now the R1 is here. Okay. And okay, so now what we have is this is R1 right here. Then this is the circumference of that circle with that radius. So this is 2 pi times R1. Okay. 2 pi times R1. And this one is the circumference of the circle when this is R2. And what I want this to be is a spot kind of halfway in between. So R is going to be the average of R1 and R2. And so then this would be 2 pi times that R. Okay, so we'll come back to that purple one in a minute. So let's find the area of these two pieces and then subtract. So the first bigger area is pi R1 L1. Okay, so remember we just said that the area of a sector is pi times the radius, which is, well, of the cone, it's going to be the lateral surface area is pi times the radius of the cone times the lateral slant height, which is L. So the L here times pi times this bigger radius here. Okay, and so that's going to give us the area of the big one. The area of the little one is pi times R2 times L2. Again, let R just be the average of R1 and R2. So R is R1 plus R2 divided by 2. Let S be the length of the original segment. That's going to be the red length here or here. Okay. Now, from this picture here, we get some similar right triangles here. So, for example, we get L2 over R2 is the same as L1 over R1, or L2 over R2 is the same as L2 plus S over R1, which is what I have right there. All right, now we'll just do a little algebra here. Let's see here. What are we going to do first? We're going to basically multiply both sides by, from the first to the last equality, multiply both sides by R1 and R2, or cross multiply. So you get R1 times L2, and you get R2 times this sum here, L2 plus S. Distribute. We get R1 times L2 equals R2 L2 plus S R2. All right, I'm going to solve for SR2, so the SR2 is here. Subtract R2 L2 from both sides. Factor out the L2. We get R1 minus R2 times L2 is S times R2. All right, so what's our area? Now, our area is pi R1 L1 minus pi R2 L2. Factor the pi out, and we get R1 L1 minus R2 L2. L1 is the longer one, so that's S plus L2. Distribute the R1. Well, yeah, this is R1S times R1 L2 minus R2 L2. That should have a sub 1 right there. Let's fix that. Okay, now let's see, what do I do? Okay, over here I factored out the L2, and this expression here is exactly what we said was S times R2. Well, now they both have an S, so I can factor that out, and I get R1 plus R2. But R1 plus R2 is twice what we said little r is. So divide this by 2, we get S, or we get R. Let me do this. So notice what we end up with. We get 2 pi times R times S. Well, 2 pi R is exactly what you get if you take the midpoint of this line segment here that we're rotating and rotate it around. It's that path that it takes, which is 2 pi R. It's that circumference taken by that point right in the middle of this S as it goes around. And then we take that times the length of the S. Okay, so that's an easier way to remember it once we got through all these steps. So it's just the length of this segment times how far the midpoint travels, which is 2 pi R. Now, what if we, now let's go to producing a surface of revolution now. So let's go back to the app. Let's see, I'm going to do 3 square root of x plus 2. So I'm going to go back to this app, and when I look at 3 square root of x plus 2, for example, and let's see, just so that I'll match the notes, let me see where I had it going. 0 to 6. Okay, and say from 0 to 6. Okay, so we're looking at this right here, and we're going to rotate around or revolve around the x-axis. Now again, if I just take this a line segment then, which goes from the end of this to the end, it's a secant line segment, then we get a shape that we just figured out how to do the volume of, or the surface area of, right? Cone minus a cone. But what I can do to make this more approximate the curve is I can do exactly what we would do when we did arc length. I'm going to take this and say, now go up to 2, and now I have 2 points. These 2 points are on the curve. So the actual square root curve is going through these dots here, but it's smooth and it's concave down, right? And so now what do I get? Well, I get 2 pieces, so it looks like this, but each one of these pieces is the kind of shape that we just found the surface area of. And then I could do that for more pieces. Here it is for 3 pieces, right? And then 4. All these are little line segments that we're rotating, so we get little pieces of a cone. And then another one, 5 and 6 and 7, and we can go on up. Here this will go up to like 100. And now this is very, very close to what the curve looks like. And we get this is what the shape looks like. So it's basically to kind of see what that's going. So let me go back to a really small one. Let's say, let's just go back to say 3 and slide it so you can see what's happening. So you can see it's pieces of cones put together. But if I do more and more and more of those pieces, it gets closer and closer to what we get by actually taking a smooth curve and going around. So that's the basic idea of what we want to do. Okay, so here's our function, here's our interval, okay, and there's with 3. And so what do we get? Well, for each one of these, for different values of n, what we're going to get getting is a type of a Riemann sum. We're going to take our interval from a to b, divide it up into n equal pieces. So delta x is b minus a over n is the width of each of those pieces. So that's the change in x going from any one of these points to the next one. We'll let x of k be a plus k minus a half delta x. So we're choosing the x value in the middle of each of these line segments. That's the x value that we're looking for. Remember, that's what we wanted to do. We wanted the value in the middle of the line segment up here. Okay. And of course, then delta y, how much the y changes is just, well, if the x is in the middle, x of k is in the middle, we have to back up a delta x to get the one at the left end, and go forward a delta x, half a delta x, excuse me. Go forward half a delta x to get the y, the x on the right side, find its y by plugging in the function. Similarly, go back a half a delta x to get the x on the other left end, do its y. The difference in those two is the delta y. Okay, it's very similar to what we did in doing the arc length setup. So what do we end up with? We do r, the radius of whatever that x value is. Now it depends on what we're doing. If we're just revolving around the y-axis, that radius is just, well, the absolute value of the function, right? It's just f of x of k, an absolute value. Okay. But what do we want to add up? We want to add up the length of that segment. I'm going to call the length of that segment delta s sub k. And then we get 2 pi times the radius times the length of the segment for each of these little bitty segments. Each of those lengths of the segments I'm going to call a delta s sub k. The radius I'm going to call r of x sub k. Well, wait a minute. Delta s sub k is the square root of 1 plus delta yk over delta x squared, and then square root, square root, and then delta x. That's exactly what we did back when we were doing with arc length. So review that video if you want to remember how we did all that. It's basically just a Pythagorean theorem. Well, this is a Riemann sum that would find each of these, like in this case, these three pieces of cylinders, find their areas and add them up. Well, we get a better and better approximation as we saw we let n get bigger and bigger and bigger. And so here's one with 100 showing. So we get exact value if we let the n go to infinity. Of course, as n goes to infinity, this ds or delta s becomes the square root of 1 plus dy over dx squared dx. This r is just r as a function of x. The 2 pi is a constant. I bring it out front. And these are our x values. So let's work this out, say, for this example. So here's the shape, more or less, that we're looking for, finding that surface area. So you see that illustrated. Okay. So this is our basic formula. Okay, so what are we going to need? We're going to need to figure out what the radius is. So we're revolving around the x-axis, so the radius is just y, which is the x. So the radius is y, or 3 square root of x plus 2. And the but y is 3 square root of x plus 2, or 3x to the 1/2 plus 2, and we need to find the derivative. So I wrote it in this power function form to find the derivative. 1/2 times 3 is 3/2. Subtract 1 from the power, it goes negative 1/2. Derivative of 2 is 0. So another way to write this is 3 over 2 square root of x. So either one of those is a pretty good way to write it. Now we want to square it. So when we square that, we get 9 over 4x. And so we want 1. So here's our basic setup. Is the area is 2 pi, the integral of a to b of r ds. ds is the square root of 1 plus the derivative of y squared, derivative of y with respect to x squared dx. That derivative squared we found out was 9 over 4x. And r is just the value here, so it's that. And so I can do this now with technology. I just plugged it in a TI Inspire, and it gave me this expression here. It's running off here, but you can see the rest of it here, which is what I've written down here, some complicated thing. Or I can get it to approximate that, and it's about 379.6. Okay, so we can use technology then to approximate it. Okay. If you want to try, it might be very difficult to find that by hand, but I've got it worked out here. So hopefully that gives you an introduction to why we set these integrals up this way for surface area of revolution, and we've seen an example set up and at least worked out with the CAS calculator. Here's another example at the bottom. We'll come back in our next video and go over this one and maybe another example. So I'll give you a chance to practice a little more and try some more yourself. See you on the next video.